Way out in the cosmos, in the constellation Auriga, there's a mystery waiting to be solved. And our crime scene? A massive cluster of stars. The big question isn't about how they died, but how they've lived. More specifically, how old are they? Today we're going to crack the case by unlocking a cosmic clock hidden deep inside a star cluster called Messier 37. Okay, so let's just jump right into it. How in the world do you figure out a star's age? I mean, you can't just ask it, right? For a star that's just out there on its own, it's incredibly difficult. But astronomers, they have this really clever trick up their sleeve, a method that literally turns a star's spin into a ticking clock. And it's called gyrochronology. Okay, think of a star like a spinning top. When it's young, it's just whipping around, spinning super fast. But over millions, even billions of years, it starts to slow down, mostly thanks to its magnetic field. So, if you can measure how fast it's spinning, you can get a really good estimate of its age. It's an absolutely brilliant cosmic clock. But, of course, there's a catch. Any clock, whether it's on your phone or hanging out in the cosmos, is pretty useless unless it's calibrated right. You've got to know that when the clock reads a certain speed, it means a specific age. And for the longest time, astronomers had this huge, gaping hole in their calibration data. So, to solve this mystery, they needed the perfect laboratory, a place packed with thousands of stars that were all born at the exact same time, a perfect control group. And that's where our celestial crime scene comes in, the open star cluster, Messier 37. And here it is. I mean, just look at that. This gorgeous collection of stars is M37. It's what's known as an open cluster, which is really just a big group of stars that all formed from the same giant cloud of gas and dust. They're basically cosmic siblings, all sharing the same birthday. And this cluster is about 4,500 light years away from us. Now, to put that into perspective for you, the light we're seeing in this picture tonight actually left those stars right around the time the Great Pyramids were being built in Egypt. Kind of wild, right? So what makes M37 so important is its age, 550 million years old. See, it's not a young baby cluster, but it's not ancient either. It's perfectly middle-aged. And this age filled a critical blind spot for astronomers, bridging the gap between what we knew about younger star clusters and much older ones. And we're not talking about just a few stars here. M37 has an estimated 4,000 members. That's 4,000 independent data points, 4,000 witnesses, all telling the same story about what it's like to be a star at exactly 550 million years old. So, with the perfect laboratory identified, how did the astronomers actually conduct their investigation? Well, they mounted what was basically a 20-night cosmic stakeout, gathering all the evidence they could from thousands of light years away. Here's the play-by-play. Using the powerful MMT 6.5-meter telescope, a team of astronomers just stared at the cluster, taking over 4,000 images. What they were looking for were these tiny, irregular dips in starlight. These dips are caused by huge, dark star spots, kind of like our sun's sunspots, that rotate in and out of view. By timing those dips, they could calculate the exact rotation speed for 575 different stars in that cluster. And this is how they knew which stars to watch. By plotting out a star's color against its brightness, they could easily pick out the true members of the cluster, that's that dense band of points you see, and ignore all the random background stars. The black dots, those are the ones they put under the microscope. And the stakeout? It was a massive success. The thousands of images and all that careful analysis, it started to reveal the cluster's deepest secrets. The clues were finally coming to light. You know, one of the research papers pointed out something that's actually pretty surprising. For all the times astronomers have looked at M37, no one had ever done a really detailed chemical analysis. And that was a huge missing piece of the puzzle. I mean, you can't really calibrate a clock if you don't even know what it's made of. So the first thing the team did was get that chemical fingerprint. And the results were fantastic. Turns out M37's metallicity, which is just a fancy word for the amount of elements heavier than hydrogen and helium, is almost identical to our sun. This was huge because it confirmed M37 wasn't some weird exotic outlier, it was a perfect average benchmark for stars just like ours. Okay, so with the chemistry all settled, they dug into the rotation data, and boom, a clear, powerful pattern just jumped right out. Just like the theories predicted, a star's rotation speed was tightly linked to its mass. So inside this 550 million-year-old cluster, the The more massive stars were consistently spinning faster than their smaller, less massive siblings. And this fits perfectly into the bigger picture of how stars age. If you look at the stars in a young cluster like the Pleiades, then compare them to middle-aged M37 and then to the older Hyades cluster, you see this beautiful, predictable spin down. The cosmic clock is ticking, and M37 provided that crucial tick right smack in the middle. But, like any great investigation, just when you think you've got it all figured out, there's a twist. The evidence from M37 didn't just confirm what we thought we knew. It actually challenged our theories in a really specific way. So here's the discrepancy. The standard models, the theories, they predicted that by 550 million years old, stars of a similar mass should have all kind of settled down to a very uniform rotation speed. But the actual observations of M37 showed something else entirely, a much wider spread of spin rates than anyone expected, especially for stars just a little bit less massive than our Sun. They just weren't behaving the way the models predicted.
Now, this doesn't mean that gyrochronology is broken. Not at all. In fact, this is exactly how science is supposed to work. The observation doesn't throw out the theory. It helps us refine it. The clues from M37 are forcing scientists to go back and tweak their models to account for this extra messiness. It's making the cosmic clock more precise than ever.
So, what's the bottom line here? Well, we've learned that a star's spin is a fantastic cosmic clock. We've seen that the cluster M37 was the perfect middle-aged laboratory to help us calibrate it. And the data gathered there didn't break our theories. It made them stronger, reminding us that science is always a process of investigating, learning, and refining our picture of the universe. The investigation of M37 has given us a new, sharper understanding of how stars like our own Sun evolve over time. It filled a really critical gap in our knowledge. But it definitely leaves you wondering, doesn't it? With countless other clusters scattered across the galaxy, each one a snapshot of a different age and a different time, what other secrets are just waiting to be uncovered in the starlight?